continuing. So let's talk about waxes. Waxes are found on the surface of fruits, on the leaves and stems of plants. They help prevent loss of water and damage from pests. Waxes on the skin and fur and feathers of animals actually provides a waterproof coating. Um, Bees use wax to protect their honey. I actually learned that honey is just the nectar, or it's the nectar that the bees got from the flowers, and they just hold it in their mouths and pass it to each other mouth to mouth until they evaporate most of the water from it, at which point it's really sticky and high in sugar, so that's honey. They have special honey stomachs where they hold this honey as they transport it around to each other. Sometimes they'll even divert some of it into their stomach so that they can eat it, but for the most part, they just run around with it, giving it to each other until it gets really thick and honey-like. Kind of gross, but honey tastes so yummy. The goal here, draw condensed structural and line angle formulas for the wax or triacylglycerol produced by the reactions of fatty acids with alcohols or glycerol. So yeah, we talked about bees for a little bit, but waxes are esters of long-chain fatty acids and long-chain alcohols, each containing between 14 to 30 carbon atoms. So you can see beeswax, for example, would be made up of a 14, 15, 16 carbon fatty acid and a 30 carbon alcohol. It's a big one. All of these look like they're the 30, oh, that one's a 30 carbon alcohol. This one's 19, 20, a 20 carbon alcohol with a 20 carbon fatty acid. Jojoba wax. Carnauba wax. I don't think I can say that right. Beeswax. So that's waxes. Waxes is short. Now let's talk about triglycerides. So in the body, fatty acids are stored as triglycerides or triacylglycerols. So these are, again, esters of glycerol, the trihydroxy alcohol. You can kind of see it here. Not really. You see the ester bond here. But again, formed when those three hydroxyl groups of the glycerol each react with their own fatty acid. And so then we just change the name glycerol to glycerol. So triacylglycerol, because it's got three of those fatty acid chains. So more of a reaction type schematic here. Actually, let's talk a little bit about the general formula for triglycerols. So they consist of the three hydroxyl groups, the three fatty acids. The one I'm showing here is actually stearic acid. So these are three stearic acids. So when we name these, not that you'll have to, but the glycerol changes to glycerol, and if you knew the name of the fatty acid, we would change that to a carboxylate name. So this one being stearic acid would become, I can't spell, stearate. Stearic acid becomes stearate. Well, if we were to hydrolyze it. I think this is glycerol tristearate is what I'm trying to say, if we were naming this. Glycerol tristearate. Oh, glycerol tristearate. I wasn't too far off. Good job. Good job myself. And you heard that. Glycerol here. You can see now the functional group, the OHs. So we've looked at this reaction before. Reaction of carboxylic acids to form esters would have been in the last chapter. And so we lose a water molecule here each time. And we can form our triglycerol. Now we don't have to have the same fatty acid every time. Let me show you a different fatty acid. So here's a condensed stearic with a condensed oleic and a condensed palmitic. Condensed because we've got the short notation. Don't try to, draw these all the way out. You'll get too far. I can't even do it without kind of trailing off. But we can make triglycerides that have different fatty acids in them, like a mixed triglycerol. Um, these guys are the major source of energy for animals, triglycerols. Animals that hibernate, they eat large amounts of plants and seeds and nuts that are high in calories, or in other words, high in, well, I was gonna put a big arrow and then write this word right here. So they're just high in triglycerols, right? And then as the external temp drops, the animal goes into hibernation, body temperature drops, reducing the cellular activity, respiration, heart rate, and all that stuff. And during hibernation, that stored fat in the form of triglycerols um, becomes their energy source. Your body's able to turn triglycerols into carbon or sugars so that it can use as energy. But yeah, it needs to eat a lot of high calorie food. Polar bears would need to store a lot of that energy prior to hibernating. Here, you would need to look this up, right? You'd have to count out how many carbons are in each of these to be able to really answer this. Don't forget this carbon, right? That's part of it. See if you can guess or answer what are the names of these fatty acids. So pause it, look those up, give it a shot. 18 carbons stearic, 18 carbons with a double bond, oleic, and then this one is 14 carbons. Here's a chance for you to draw. So draw the condensed structural formula for the triacylglycerol containing 3 molecules of palmitoleic acid. Palmitoleic acid is a monounsaturated acid. So you have to look that one up to see where the double bond is. Typically, you would want to arrange it so that you can get rid of your waters and form your ester bond. The O from the alcohol is typically the one that sticks around. So you get something like this. So, yeah, drawing these it's good practice. And then hydrolyzing them, going back and putting the water back in, splitting these guys up into their two component parts. Draw the condensed structural formula for the triacylglycerol containing 3 molecules of myristic acid. Remember, that's the 14 carbon one. No double bonds. You should be able to do it without even looking it up. 14 and O. So start by drawing that fatty acid and then connect 3 of them together. So it looks something like that. Sometimes, just for ease of kind of drawing this, you can flip this one around, have it pointing out this way. So your double bond is up like that. So they don't get in the way. I don't know. When you're drawing them, sometimes they can get crowded. Let's talk about melting point of fats and oils. So let's just compare them. Fat, oil. A fat is usually solid at room temp. I'm going to say 25 degrees. An oil, usually liquid. A fat usually comes from an animal source. Meat, whole milk, butter, cheese, something that would be from an animal. Oil, usually obtained from a plant source, like corn or olive. Oils, as you can see here, olive and peanut oils, they're monounsaturated because they contain a large amount of oleic acid. Oleic acid is a monounsaturated fatty acid. So it's because they have that fatty acid that their triglycerols or oils are liquid. Corn, cottonseed, safflower, sunflower, these are polyunsaturated, and they have more than one double bond in them. So they're also, again, it's the fatty acid that you contain that makes you an oil compared to a fat. Now, palm and coconut oils are solid because they have mostly saturated fatty acids. Saturated fatty acids, again, have higher melting points because they can pack together better. I have a nice table that I'm going to show you right now. So you can See, beef tallow, or I guess lard, coconut, butter, these things are all solids. And you can see the percentage of saturated to unsaturated fats in blue here. The majority, well, almost in beef tallow, is saturated fats, with some monounsaturated fats spread around in there. Coconut butter or coconut fat only has some amount of monounsaturated, but mostly saturated. Look at the liquid side when you flip that. The blue, remember, is the saturated. They all have very low amounts of saturated and higher amounts of either polyunsaturated or monounsaturated. So depending on what percentage of fats that you make or that you're storing are saturated or unsaturated will determine the physical properties of your, I guess, your physical state. Will determine your liquid or solid state. So let's get into some of the chemical properties then. Many soft margarines, stick margarines, and solid shortenings are actually produced by the partial hydrogenation of vegetable oils. So we get these solids from the oils. That's how we get solids that are, let's say, healthier, quote unquote, than just solid fats. You could eat lard or bacon fat, but you could also just use margarine, which isn't made from the same source. Now, we're taking unsaturated hydrocarbons and saturating them is essentially what we're doing. We're making them less crooked looking molecules so that they will pack together nicer so that they can be more solid at that given temperature. So one of the things that we're going to look at is this hydrogenation, where we add hydrogen gas or we reduce the double bond. We'll also look at hydrolysis and saponification. Hydrolysis is the general term. Saponification is the base catalyzed hydrolysis. But we'll look at the products that form. So first we've got triglycerols here. Triglycerols, when we react them with hydrogen gas, we can either do this by bubbling hydrogen gas through the heated oil, typically in the presence of a catalyst, nickel, platinum, palladium, something like that. The double bonds in the unsaturated fatty acid will react with the hydrogen gas to produce carbon-carbon single bonds. And so then we get these partially hydrogenated liquid vegetable oils get turned into soft or semi-solid fats. And again, the addition of hydrogen is stopped before all the double bonds become completely saturated, because at that point you might as well be eating bacon fat or something that just has a high saturated fat content. The goal here is not to introduce so much more saturated fat. It's just to introduce enough that the state of the substance changes. You're much more inclined to spread a little bit of margarine on your bread than to dip your bread in a bowl of olive oil, for example. Though you could do that, and that's probably healthier. The more saturated product has the higher melting point, thus it becomes a solid. So, what product or products would be obtained from the complete hydrogenation of glycerol trioleate? So, you're going to have to look up, remember, trioleate here, the name, kind of reverse engineer it, trioleate, so there's three of the same oleate. Oleate is the carboxylate, so this would be oleic acids. So there would be 3 oleic acids. I guess I answered the question for you, didn't I? No, I'm telling you what we're starting with. We're starting with trioleate. But what would be the product from the complete hydrogenation? So go ahead and pause that and give it a shot. If you said glycerol and 3 stearic acids, you're wrong. While stearic acid is the unsaturated version of oleic acid, there's no hydrolysis happening here. This is just changing the triglyceride from a low melting point to a high melting point to a high melting point state. So glycerol tristearate is what happens when trioleate is reduced. Glycerol and 3 stearic acids would happen if after this was done, then we hydrolyzed it. And glycerol and 3-oleic acids would be what would happen if we just hydrolyzed. So hydrolyzed, this would be hydrogenate and hydrolyze. There's an R in there somewhere. Doesn't matter. Glyceryl tristearate. This one's a little more fun. Draw the condensed structural formula for the product of glyceryl tripalmitoleate. Yikes. Palmitoleate. Tripalmitoleate. That undergoes hydrogenation. So here, we know what's going to happen. The double bonds are going to be reduced. So you would just be drawing the product of that hydrogenation. Now, just because we don't do complete hydrogenation doesn't mean that you only hydrogenate these two and you leave this one alone. It just means that of all the molecules that would be in the oil, not every molecule gets reduced. In case you weren't even thinking about that, don't even worry about it. So go ahead and pause it, give that one a shot, give it a draw. You would just simply be drawing the same number of carbons. There would be no double bond. It's good practice though, drawing these. So you know where your ester bond is. You're getting familiar with the glycerol backbone. It's important when we switch it up, start looking at sphingosine and that sort of stuff. So hydrolysis. Hydrolysis is the undoing of our ester. Now we already went over this in the last chapter. You remember in the presence of acid, we get back our fatty acid and our alcohol. But in the presence of base, we get back our carboxylate salt. And our alcohol. So depending on whether it's acid or base, we're going to get different forms of our fatty acid. We'll always get the alcohol back. So here you can see in the presence of acid or with an enzyme, water gets added back into the bond. So our alcohol gets its H back, and our carboxyl gets its OH back. And so everything's back to normal. Nothing changes on the fatty acid side. Nothing changes in the glycerol backbone. We're just splitting them. That's hydrolysis. Now, saponification, the process of making soap, is just reacting fat with strong bases, like sodium hydroxide in the presence of heat. You can actually, this is if you didn't know that you could do this, there's something called potash. You take just burnt wood, and you take the ashes from the burnt wood, and you can actually get potassium from that. You can actually isolate potassium. But one of the things that you can do from it initially is that inside that ash is some basic compound of potassium carbonate and potassium hydroxide. You can actually take some ashes from a fire and add them to some bacon fat in a pot. You could be, let's say you're cooking out in the woods and you get really dirty and you want to be able to clean yourself, but you have nothing to clean yourself with. You heat up some animal fat in a pot or a pan. You add some ashes from your fire. You cook it in the stove or on the fire until it starts to froth and kind of get some suds, and then you wash yourself with it, and it's rudimentary soap. You're basically converting the fat by adding the base that we got in the ashes into, well, I don't know that you have glycerol. There will be, depends on what fats they are. They might be sphingosine, but you're going to have some glycerol or some sphingosine, but you're going to have some salts of fatty acids. And salts of fatty acids are what soap is. Sodium hydroxide gives kind of solid soaps that can be molded into different shapes. Potassium hydroxide, as I'm kind of talking about here, would give more of a liquid type soap. But essentially, this is what saponification is. It's soap making, and that's what happens that's where soap comes from. It comes from fat sources. You could even use waxes, I suppose. And so here, because it's a strong base, remember we're going to get back our alcohol. So glycerol comes back. But the H doesn't get added back onto the fatty acid. We get the O back, but no H because acids don't live in base. They would get neutralized. And so the counter ion is going to be whatever came with our base, in this case sodium, but there's a negative charge on our carboxylate. And that name would be, again, the carboxylate of the fatty acid. So if this was palmitate, this is, or palmitic acid, this would be palmitate, sodium palmitate. Saponification, making soap. So we kind of looked at both. The acid hydrolysis or enzyme hydrolysis gives you back your acid and your alcohol. And then the saponification gives you back the the salt of your fatty acid and our alcohol. So I guess this sort of summarizes those reactions right here. So the three reactions for our triglycerides are the hydrogenation, the hydrolysis, let's call it acid, and then the hydrolysis, let's call it base, or you can call it saponification. That's the real name for it. But it's base hydrolysis. This is a nice resource too because it tells you what you're getting at the end. All right, learning check. Write the balanced chemical equation for the reaction catalyzed by the enzyme lipase that hydrolyzes glyceryl trilaurate during the digestion process. So you've got the formula here. You don't have to look up laurinic acid. This would be the balanced chemical equation. You start with the structure. You got your waters. And now you're going to show the glycerol and the three fatty acids that we get from it. And in this case, they will be fatty acids because this is acid hydrolysis. How do you know? Because there's no base, and it says enzyme lipase. So remember, acid hydrolysis or enzymatic. So that's what you should get. 12 carbon fatty acids with their hydroxyls and our glycerol. Practice one that has saponification though. Again, those are usually something I'll write on the test. All right, I'm going to save this for part 3.